there is a room downstairs on the first floor with table that is for you. So if you need a place where to work, where to do exercise, where to meet, everything is downstairs, first floor.
Okay. Can everyone hear me? Yes. All right, so we want to continue with the slow roll inflation. And so what did we say before? We said that if we consider a scalar field with a potential which is flat enough, then we are going to get this phase of a slowly rolling a scalar field. And during that phase, we are near the center. We have a near the center phase that we call it inflation. So let us see what more closely what are the conditions to realize this phase, because obviously if I write the normal potential and consider the scalar field in this potential excited the scalar field, I'm not going to satisfy this condition of the slow rolling. So okay, we are going back to the model that we had. So we write the action. Let me write the action for just for a only time-dependent, spatially homogeneous field. So I do the decomposition here. D3x, there will be a factor of a cubed, phi dot squared, the factor of 1/2. Minus v of phi. And so we write the equations of, derive the equation of motion from this action. I get phi double dot plus 3h phi dot plus v prime is equal to 0. But here v prime means derivative of v with respect to, so this is v of phi, and v prime is derivative of v of phi with respect to the field. Okay, now we said that we want to consider a phase in which the field is slowly rolling. If it is slowly rolling, what does it mean? It means that the time derivatives of the time derivatives of phi are going to be small. So I'm going to drop the second time derivative of phi, approximate the equation by only this term, these two terms. So the approximation is, I assume that phi double dot is much less than h phi dot. And therefore, we get phi dot equals minus v prime over 3h. Well, of course, this is an approximation, so this is not a perfect equality, it's an approximate equality. So if I can ignore phi double dot, I get this solution. And so now I should check as a couple of conditions. First of all, I want to check that if I consider this model, whether I'm going to get this nearly de Sitter phase, or whether I'm going to get W close to -1. How do we do that? So we go back to the energy density, the expressions for the energy density and pressure. So if we go back there, if I divide, so I wrote the expressions in the previous lecture. If I take the ratio of P over rho of those expressions that we had in the previous lecture, this is going to be -1. And if I assume that the contribution of the kinetic energy is small, so if it was 0, if it was only potential, we would get exactly -1. A constant potential would be equivalent to having CC, which is W minus. So let us assume that the kinetic energy is small because we want to be near -1. If I assume that it is small, then I can expand the denominator. So what is going to appear here is, so I get -1 plus phi dot squared over V. Right? And so the requirement that W is near -1 is that phi dot squared over V has to be much less than 1. So we want to check whether this condition is satisfied. Or another way of seeing this, so this was W, which we approximated here. Another way of seeing it is that if I look at the Friedmann equation, From Friedman equation, we can go to another Friedman equation, which is given by taking the time derivative of this. And if we do that, we can find an expression for H dot. H dot is going to be given by minus, so I'm just taking the derivative of this and using energy conservation equation. I get H dot equals 4 pi g times rho plus p. After I take the derivative of this and use the conservation of energy, the fact that rho dot is given by minus 3h times rho plus p. So from these two equations, I derive this. Now for a scalar field, rho plus p is just phi dot squared. So here I get 4 pi g times phi dot squared. And we want to define something that is got the slow roll parameter, which tells us how close we are to the sitter. How do we do it? By comparing the variations of h. Remember, h dot is negative if we satisfy the null energy condition. So I take its absolute value, which is minus h dot. Also, you can see it from here that in this particular case, it is negative. I define this slow roll parameter by comparing the rate of the change of h, the expansion parameter, to h squared. So the requirement of being near the sitter is equivalent to the requirement that this quantity is small. Now, what is this quantity? This quantity is, so for the numerator, I can use this equation. So this epsilon is given by 4 pi g times phi dot squared. And then in the denominator, I have h squared, which is given by 8 pi g over 3 times rho. But we are assuming that the kinetic energy is small compared to the potential, so rho is dominated by the potential. So to leading order in the ratio of the kinetic energy to the potential energy, I can just replace the rho by v. So I get this ratio. All right, so then what do we do with that? We plug in this slow roll solution in this expression. So this gives me 4 pi g. Phi dot squared is v prime squared divided by, now I have 8 pi g. Well, let me cancel this 4 pi g and 8 pi g. So I just have 1 over 2 3 here, and then I will have 9 h squared v. Again, I can use the Friedman equation. This is 3. This gives me v prime m Planck squared. Sorry, m Planck v prime over v squared. Where remember, m Planck squared was defined as 1 over 8 pi g. So we get this ratio. And we want this to be much less than 1. So let us consider some examples. For instance, the easiest thing to consider is, let us take, where do I want to write it? Let's see if I can fit it here. So let's say V is just m squared phi squared. We just have a massive field. And we want to look at this ratio. So in this case, this epsilon is going to be 2 times m Planck squared over phi squared. So if I want epsilon to be much smaller than 1, I can achieve it by having phi to be much bigger than m Planck. How much bigger than m Planck, we will discuss it soon. It's determined by the number of e-folds of the inflation that we want to get in this model. But so what we see is that if we have a potential, and now you can see that if instead of m squared phi squared, I have some other power law, would be a similar story. If it was something like phi to the p, then if I wanted to look at this ratio, I would get something, again, like m squared over phi squared with some prefactor that depends on this power law. But as long as that power is some order 1 number, is the same story. If I have simple power law, I need phi, the field, to be much larger than m Planck to get a small epsilon, or to be close to the theta. So if I look at this potential, this power law potential, the idea is that if I go high up on the potential, then I'm going to satisfy this condition, this slow roll condition, and I'll be near the theta. However, I have to check another thing, another assumption that we made. So we made this assumption that phi double dot is much less than h phi dot. So a consistency check of all of this discussion is that on this solution that I have found, this condition is satisfied. So let us evaluate phi double dot on this solution. So what is phi double dot? It is we have to take the time derivative of minus v prime over 3h. This is minus 1 over 3h v double prime times phi dot plus v prime h dot over 3h squared. Now what I do is I take this expression and let's see, what should we do with it? Let's first look at this this by v prime over 3h. I can write it as, so this is again v double prime over 3h phi dot. This term I can write as minus h dot over h times phi dot, because phi dot is minus v prime over 3h, so v prime over 3h is minus phi dot. So for instance, if I look at phi double dot divided by h phi dot, what do I get? This is going to be v double prime over 3h squared minus h dot over h squared. So we want this ratio to be much less than 1. This part we already We already talked about. This is exactly epsilon. So we know how to make it small. So if this is a small, then for this ratio to be small, we need this another condition, that V double prime over 3h squared its absolute value has to be much less than 1. This other combination is called it's called a second slow roll parameter. So this V double prime over 3h squared. And we want this to be much less than 1 if we take its absolute value. So what does it mean? For instance, if I have m squared phi squared, so this eta is V double prime over 3h squared. I can again express this 3h squared as, using Friedman equation, as 8 pi g times V. So this ratio for m squared phi squared, this ratio is going to be twice m Planck squared over phi squared. So the same requirement that made epsilon, the first slow roll parameter, to be small, it makes the second one to be small too. And again, this is a generic situation for power law potentials. So once I go far up on these potentials to super Planckian waves for the phi field, then the slow roll both the slow roll conditions are being satisfied. And therefore, it is justified. This is a self-consistent solution of this equation. Now, an important property of this solution is that it's an attractor solution, meaning that if I am not satisfying these conditions, I'm going to exponentially fast converge to this solution if I'm satisfying the conditions. That is, if phi is much larger than m Planck. So this is important. How do we see that? So here we said that we take time derivatives to be small, and therefore we neglect second time derivatives, and the phi dot is driven by the slope of the potential. So the potential is relatively flat, and then it slowly moves down the field, but there is Hubble friction. That's how we can think about this equation. It's like an equation of motion for a particle in a potential, except that there is a friction there. And then because of the friction, it moves on this trajectory. Now, let's assume that we don't satisfy this condition. Therefore, this 3h phi dot, for instance, is much larger than phi v prime, and also this phi double prime. So the slope of the potential is irrelevant. I can just look at this system. Yeah. The Planck mass to Hubble constant where? Here? Here? So here I had h squared, right? Is this what you are asking about?
And then you define there as here.
Here?
Okay, yes.
Yeah, so there is Planck. So this equation can be written as h squared equals rho divided by 3 m Planck squared.
Why should there be a relation between Planck mass and expansion rate of the universe at that time?
Well, the relation is that well, there is a rho here, right? So it's just the fact that you have matter, which is here is contained in this rho, right? You have matter fields that have some energy density. And through Einstein equations, that those matter fields which have some energy or energy density or energy momentum tensor, they back react on geometry. So Einstein equation tells us how energy in the matter sector tells us or determines the behavior of geometry. But this back reaction of matter on geometry requires some proportionality constant. There is a coupling constant in this equation, which is G Newton, right? That's G Newton that sits here. And M Planck is just defined in terms of G Newton. It's just a constant of nature that is, I just defined it as 1/8 pi m G Newton. By the way, I never mentioned this, but I took it for granted that we are in natural units, meaning that h bar and c are equal to 1. So 1/8 g has the dimension of mass square. That's how they get related. The Planck scale tells us how what is the strength of gravity or the weakness of gravity. How if Planck scale goes to infinity, matter fields do not back react on geometry. If Planck scale is lower, matter fields back react more. It's the It's the coupling of matter to gravity. Other questions? Okay, so where are we? We want to see that this solution that we found, this slow roll solution, is an attractor solution. To verify it, I'm considering an initial condition in which phi dot is fast. So I'm not satisfying this attractor, this slow roll condition. I'm even dropping the potential. And then I will be dealing with this equation. But then what is the solution to this equation? One is that phi dot is equal to 0. So that is not fast. The other one in which I can have large phi dot would be phi dot going proportional to 1/a cubed. And remember that a, the scale factor, is growing exponentially during inflation. So what happens is that if we start away from the slow roll solution, then phi dot goes down exponentially fast until we get to the point in which we cannot ignore the potential anymore. And then we'll get that solution. So if we want to look at the phase diagram, what happens on this slow roll solution, on this attractor solution, is that phi dot is uniquely fixed in terms of phi. Normally, in this dynamical problem, phi and phi dot are independent variables. When I want to solve, for instance, for motion of a particle, I should give x and x dot, and then I find the trajectory. However, the property of attractor is that on the attractor, phi or x uniquely determines phi dot. So that's what's happening there. So then we have this attractor solutions that does something like this. Of course, it's attractor when we have large values of phi. where these conditions are satisfied. And then if we start away from it, we just exponentially fast converge to it. Now let us ask how big this phi has to be. So because so far our discussion was qualitative. We wanted to just say that we want to be near the seater. But we need to know how close to the seater we want to be. And the condition that determines that, at least once I fix the potential like this, is that we needed some number of e-foldings of the inflation. And as you can see from here, what happens is that what happens in this attractor solution, so I have this phi fit that is rolling down the potential. And I'm satisfying the conditions as long as phi is much larger than m Planck. Say m Planck is here. So as it rolls down, these conditions are satisfied. I have nearly the seater face until I get to phi of order m Planck, and then I stop having inflation. That would be basically the end of inflation, when epsilon becomes of order 1. And the duration of inflation, which determines the number of e-folds, is determined by the initial value of phi that I start with. So the farther away I start, the longer it takes until it arrives at the bottom. The longer it takes, more expansion, more number of e-folds. So how do we determine that? We remember that the number of e-folds of inflation is the integral of h times dt. This tells me that how much the universe is expanding. Because let me just say that the NE dt is just defined by the time derivatives of the log of A. So we want to say how the logarithm of A is changing with time. And then we integrate that equation. So now let us evaluate that expression. So this was the definition. We can do that. So this the bounds of this integral from Ti to T, what I call Tf, T at the end of inflation. And now I can do a change of variables, replace T by phi. So then I will get, I write this dt as d phi over phi dot. Now I'm integrating from phi initial to phi final. And then I can use this Lorol solution here. So I'll have phi dot, which is minus v prime over 3h. So I get 3h squared d phi divided by v prime with the minus sign, phi I to phi f. And then again, 3h squared is v over m Planck squared. So I get minus 1 over m Planck squared, phi I, phi f, v d phi over v prime. Okay, now we can evaluate this in some. So note that this v prime over v is closely related to this Lorol parameter, right? This Lorol parameter was something like v prime over v squared times m Planck. But let's consider some concrete model like m squared phi squared again. And if we do that, then this V over V prime is just going to give us -1. So this gives us a factor of 2, 1 over 2 m Planck squared integral phi I, phi f, phi d phi. So we get NE equals 1 over 4 m Planck squared times phi I squared minus phi f squared. Now let us say we want to end the inflation when epsilon is 1. So here we are. We have m squared phi squared, and epsilon for m squared phi squared is given by this expression. So if we want epsilon to be 1, it tells us that phi squared at the end of inflation has to be twice m Planck squared. So this is phi I squared over 4 m Planck squared minus 1 over 2. Now, we have a condition on this number of E-folds, right? We want it to be larger than 60 to solve the problems that we invented inflation for. So if NE has to be larger than 60, then we can easily see that this phi I has to be something over the 16 m Planck, or larger than something over the 16 m Planck. And if we repeat the exercise for other potentials which are simple power laws, we are going to discover a similar thing. So up to all of this analysis goes through, except that there will be some dependence on this power of phi on which we depend. So we will get some order 1 number here, which might be different from 2. But the general fact that we need large phi excursion would be correct in this class of models. Yes?
Maybe I lost the thing that there are no bounds on the mass. Is that right?
No bound on the mass of the, yes, thank you for asking, because I wanted to mention it. As you see, all of these conditions, they never constrain the mass of the inflaton field in this model. It's always canceled from these expressions. So it's true, yes. However, later we are going to talk about the theory of fluctuations. And then we will see that those are sensitive to the scale of inflation. So this mass, what it does is that, of course, it determines the value, the absolute value of the energy density, right? If I change for a fixed phi, for instance, there we discovered that phi has to be 16 m Planck at the beginning of inflation. For that fixed phi, if I change the mass of the inflaton, the energy density will change. If the energy density changes, the Hubble during inflation itself will change. And then we will see that the prediction of inflation for the amplitude of fluctuations does depend on the scale of inflation, or this h. And that will fix m for us. Now, of course, one does not have to be limited to these simple power law potentials. the idea of the inflation was very general. The idea was that whenever I have a potential that is sufficiently flat, I will have a phase which is close to the center. The simplicity of this parallel potential is that once field moves far away, it automatically satisfies those conditions. Although in terms of pictures, it might not look very flat as they go far away. But flat properly defined is satisfied once they go far away. On the other hand, nobody stops me from considering a potential that is not a power law and it satisfies the slow roll condition. The only point is I have to put a new scale in the potential. So I should consider a V of phi that is sufficiently flat, but then at the end, instead of naturally going down, as these parallel potentials do, it has a scale in it. So at some point, it turns and goes down. Remember, we want this inflating phase to finish. Now, in the parallel cases, it would finish automatically. It would put it up there, and it would roll down. Here, in order for it to finish, this flat plateau that I have has to end by designing the potential. So I couldn't just continue this flat plateau. So these models are called, when we have this super Planckian field excursion, these are called large field models of inflation. Large means that phi is larger than the Planck scale. However, one can also consider small field inflations by slightly tuning the potential. Now, as I said, the predictions of inflation for the fluctuation is sensitive to the scale of inflation. So in fact, the current data is slightly disfavoring those simple power law models. We are getting more closer to models which look like this, the lower scale or smaller field range models of inflation. Any question? Yeah?
Explain a little bit more how do you see this in observation?
Say it again.
How do you differ from model to model by observing?
Yes, I am going to discuss it in more detail later. Yeah.
Okay.
Yeah, at the moment I haven't said anything. I just promise that in the future you will see. Okay, so let us talk about, if there's no other question, yes.
I would like to ask about the number of e-foldings, because we made a lot of approximations to obtain it. And I was thinking, how do you know that these approximations are sufficient? How do you know that maybe you could increase the number of the e-foldings to get a more comfortable? Do you understand, like, if you didn't do those approximations you did before to obtain the number of e-foldings, it wouldn't be more trustable to work with? And also if there is a maximum number for the e-foldings.
Okay. Yes, so right, so Obviously, yes, I did make some approximations, and if you want to be very precise about the predictions of inflation, one needs to be a bit more careful about this, determining these values. So far, this were here just to show you that I'm getting more or less than the right values. For instance, you can ask about the time it ends, this final time, and the assumptions about reheating. Those are important considerations when we talk about number of e-foldings and the precise observational signatures of any model of inflation. However, usually it happens that, and for a reason, usually it happens that these corrections will change the results that I obtain here by very small values. The corrections are usually of order percent, and this percent comes from the fact that these slow roll parameters are very small. So if you want to be precise at the percent level, then you have to work a bit harder to keep all of these slow roll corrections and I don't know, maybe slight deviations from attractor, this sort of thing. Or for instance, what happened at the beginning of inflation. Because at the beginning, you might be slightly away from the attractor. So this little details will enter if you want to ask percent level questions. Otherwise, these approximations are good. It's important to know what is the error in the approximation, or what is the precision of the approximation. And here, most of the times, that is determined by the slow roll parameters. Oh, yes, sorry. Yeah, there is a maximum not from a more maybe theoretical perspective, or maybe not even theoretical. Meaning that, of course, you could imagine that inflation started at a bigger value of phi. That didn't have to start exactly at 60 folding. Could have started much earlier. However, something happens, which is that if you take this m squared phi squared potential as an example, and you keep going farther and farther, or higher and higher on the potential, at some point you enter a phase which is called the eternal inflation phase. Eternal inflation means that what happened in this scenario is that you have this slow roll behavior that makes the inflation eventually end, right? Now, as we are going to discuss later, either later today or tomorrow, there will be quantum fluctuations of the field. And those quantum fluctuations will become larger and larger in some sense if the slow roll parameter becomes small. So at some point, as you go farther up on this potential, this epsilon parameter, slow roll parameter, becomes smaller and smaller. And then those quantum fluctuations become more and more important. In a sense, you can think of it like that. This epsilon parameter was controlling how flat is your potential in some sense, in some useful sense, I would say. As you go higher in the potential, that flatness condition is becoming satisfied better and better. At some point, it becomes so flat that the slow rolling behavior that you are getting is become irrelevant compared to the quantum fluctuations that we are going to talk about. And therefore, the field never, or the full universe will never go to the end. You will have this eternal phase of inflation in which inflation never ends. And eternal inflation is something that we haven't understood very well yet. So there are many puzzles regarding eternal inflation. So and obviously in our universe, inflation has ended. So you might even imagine that there is some eternally inflating universe, but we are obviously not in there. We are in some part that is separate. So there is the upper bound. The only upper bound that exists is that. Yes, it depends on the. Does it depend on the potential? Well, maybe not much, because so you see the condition that appears here, this is V prime of, so you have this integral of V over V prime. So what happens is that even if there is a dependent, well, yeah, I guess I don't know. I have to think a bit more about it. But yeah, I suspect there is a relation between just the number of E-folding and going in the eternal phase. But I should think more about it. Other question? Yeah.
Just continuing her question. In the morning, I think you derived an upper bound for the number of E-foldings of about 60, if I got it right. And you did this using the value of the Hubble parameter at the beginning of inflation was less than something. And I didn't understand where did it came from.
Okay. Well, so actually in the morning what I did was I derived a lower bound on the number of E-folds. So I said to solve the problems, we need at least 60 E-folding. However, to derive that, I used an upper bound on the scale of inflation. So I said HI has to be less than 10 to the minus 5 n Planck. Right? No?
But if HI is less than this, isn't the number of E-foldings less than 60?
No, there is no direct connection between HI and number of E-folds, because as long as you have this, so what is the number of E-folds? You have the scale factor. So NE was defined as the following, right? And E to the NE, the number of E-folds was A final divided by A initial, right? Now, if you have inflation, A during inflation goes as E to the HIT, right? Therefore, NE is equal to, if we have inflation, which means that we are close to the theta, if this HI is almost constant, HI is equal to, NE is equal to HI times T final minus T initial, right? But no one fixed TI and TF for us. So you can have a lower scale inflation, which means that HI is lower, but have it for a larger value of T, and then you get larger number of E-folds. So there is no direct connection between number of E-folds and the scale of inflation. For any scale of inflation, you can have as many E-folds as you want. While this condition was derived to solve the observational problems with the Big Bang cosmology. While there is another condition, NE less than some an E of, let's call it eternal. Well, you do, in fact, I don't know, you can, it's not that, it couldn't be that there is eternal inflation. Even if there is eternal inflation, we are not during that inflating phase. So that we have to be in a part that in which inflation has ended. It just means that there are many more universes in which the universe is inflating, and then it's hard to understand the situation in that case. There is something called a measure problem associated to that. Other questions? No. All right, so this, yes, so as I said, so I'm going to finish the discussion about the classical dynamics of inflation. So far it was just how the field rose. There was no mentioning of quantum mechanics so far. The only thing that I should say to finish this discussion is say a few words about reheating, the end of inflation. So of course we are now we are in some accelerated expansion phase, but this is not the inflation that I'm talking about. This inflating phase has to end, turn into a hot universe that leads to this, in which the standard model particles are in thermal equilibrium. They have some temperature. Then we have the full thermal history, and then eventually we are now back in some accelerated expansion. So this early phase of inflation has to end. And this end is called reheating. Reheating because I guess this is a relic of the time when they thought that inflation starts during some thermal phase. Then the universe becomes cold and then it reheats. So that's why they call it reheating. But now we are not necessarily thinking of inflation as happening like that. But still the name is there. Basically the idea is that when the inflation ends, we need this energy density that we had in the inflaton sector. We want this energy density to go into a standard model. Maybe not with 100% efficiency, but with enough efficiency that we get a standard model in thermal equilibrium, and then we get this radiation-dominated phase. Now, I'm not going to discuss details of this reheating. There are, of course, many models. It's not as simple as the model that I wrote for inflation. So for inflation, I just needed the scalar field with the potential, flat enough potential. Reheating is clearly much more involved, complicated. There are many possible scenarios, reheating scenarios. Just to give you an idea of how it can happen, again, let's go back to this m² phi squared case. So when the field arrives at the bottom of the potential, what it's going to do is that it's going to oscillate at the bottom. That's when the inflationary phase has ended. And now we can ask what is the description of the universe during that phase when the inflaton is oscillating at the bottom of the potential. So for that, it is useful to look at let's go back to the equation of motion. Let me write it down explicitly for the m² phi squared model. And now we want to assume that we have arrived at the bottom of the potential when the the slow roll assumption is not satisfied anymore. And the scale of inflation is very low now. Remember, the scale of inflation depends on the value of the potential. As I go lower and lower, sorry, not the scale of inflation, but the Hubble. It depends on the energy density. So as I go lower and lower, H becomes lower and lower. Eventually, this H becomes less than M. Remember, before it was larger. For instance, for m squared, phi squared, this eta parameter, second slow roll parameter, was just m squared over h squared, which was much less than 1 during inflation. At the end, it's going to be much larger than 1. So m is much larger than h. And then when m is much larger than m, now the perturbation in this equation is this term. And I can solve for phi, or find an approximate solution for phi. So how does it look like? If this term wasn't there, I would just get an oscillating solution, right? This is just a harmonic oscillator. If this one wasn't there, I would just get, say, A times e to the I mt plus its complex conjugate, because phi is a real field. Now that this term is here, then this coefficient will adiabatically very slowly changes in time. The slowness of the time dependence of this is determined by h, right? So if h was 0, then it wouldn't change. So this should be order h. Now I can plug these ansatz in the equation and use the fact that the time derivatives of A are small compared to M, because the time derivatives of A are of order h. I can plug these ansatz in the equation to get what I will get is that an equation for A which says that A dot plus 3/2 HA is equal to 0, up to corrections which go as higher time derivatives of A. So there are corrections here which go as h over m corrections that I'm dropping. And then the solution to this is that A is some constant, I don't know, some other constant, C divided by A to the 3/2. So what does the field do? What the field does is that phi of t is given by some c divided by a to the 3/2 times cosine mt. So I just randomly picked the phase of this e to the I mt to be such that I get the cosine. So I get this solution for phi, and let's see what it describes. We can look at the energy momentum tensor, or the energy density, in particular the energy density of this field with this solution. And it's not hard to see that. So this rho was what? This rho was 1/2 phi dot squared plus 1/2 m squared phi squared. And if I plug this ansatz in here, I will get 1/2 c squared c squared divided by 2a cubed. Plus again corrections which are of order h over m, which I'm dropping. So this must be familiar from the discussion of the morning. If I have some component whose energy density is diluting as 1 over a cubed, that is the way that matter is behaving. So what this solution actually describes is just a matter-dominated universe, where matter here corresponds to just these phi particles, inflaton particles. And this solution corresponds to having, so if I can define some number density of phi by dividing rho by the mass of phi. And what this solution is describing is just a number of phi particles that are sitting there and they are diluting with the expansion of the universe. A matter dominator, a dust model. In fact, this is something that will be discussed a lot in other lectures, this dust model. And in fact, this coincidence that from an oscillating scalar field we get matter domination has been used to introduce a different model for dark matter. Maybe someone might talk about it in these lectures. It's called fuzzy dark matter. So the idea is that usually when the most standard model for dark matter is to consider WIMPs, to have just heavy non-relativistic particles, which is called cold dark matter. However, you can also imagine that you have a scalar field that is oscillating at the bottom of its potential, and that also has an equation of a state that is equivalent to W equals 0. It has some differences, small differences as you go to a smaller scale, but for W cosmology is identical to matter. Anyway, so what we have here is this matter-dominated universe, which we can think of it as being made of a lot of non-relativistic phi particles sitting there. Now, if these particles are somehow coupled to a standard model, then they can decay into standard model particles. Presumably, they have a mass which is much, much larger than the masses of standard model particles. So when they decay into the standard model particles, they will be very relativistic. And therefore, depending on what is this decay rate, after some time, we will get this thermal phase in which we have a standard model at some high temperature. And then from there, the standard cosmology can continue. Any questions so far? So this was reheating. So if there is no question, then I think I can talk about fluctuations. Let us first consider instead of focusing on the case of inflation, let us first consider linear fluctuations of a field, a scalar field in general FRW. So maybe I have the action here already. No, because here I assume that it's time independent. So now we are considering a field which, sorry, there I assume that it's only time dependent, but homogeneous. Now I want to consider the situation when the field is also fluctuating in position spaces inhomogeneous. So I'm going to keep the gradients, and let me call it by this curly phi. So if we want to go back and think about inflation or inflaton, this curly phi would be fluctuations of the usual phi. And let us ignore the potential. So I'm just going to consider a massless scalar field in a general FRW. I will have minus 1 over a squared grad phi squared. And what else? I'm also assuming, just for simplicity, that we are spatially flat. So k is equal to 0. So this is the equation for the scalar. This is the action for the scalar field. The equation of motion is phi double dot plus this part is as before. Now I will get this additional piece that is that gives me 1 over a squared times Laplacian of phi is equal to 0. Now, one thing that we can immediately do when we are dealing with this problem is that you see here the action has explicit time dependence. This is scale factor here is time dependent. However, nothing depends on x. In fact, that was the defining property of our FRW cosmology. So nothing depends on x. I'm doing linearized theory, so this makes a lot of sense to work with go to momentum space, work with Fourier modes. So that's what I'm going to do. I write phi of t and x in terms of I go to the momentum space or do a Fourier transform. I write it as d3k. And I put this bar here. This means dividing by 2 pi cube. This bar is the same bar that you have in h bar, for instance, times e to the I k dot x phi k of t. And now if I expand phi in terms of these Fourier modes, then the equation becomes, of course, this equation is a PDE. There are derivatives with respect to time and space. Once I do this Fourier decomposition, it simplifies. It becomes a system of ODEs for each k. So for each k mode, I get phi k double dot minus plus 3h phi k dot plus k squared over a squared phi k is equal to 0. Now, another thing that we can do is another simplification is that we work with the conformal time. Remember, conformal time was defined to make pictures look nicer, to make light to propagate on 45 degrees. So dt was a d eta. So if I work with the conformal time, then this equation will change into phi double prime of k. Now it's k of eta. Let me even write the action in terms of the conformal time. So the action is going to be minus 1/2 d eta d3x. Sorry, there is no minus here. there's a minus if I write it as d phi squared. A to the fourth, a squared phi prime squared minus grad phi squared. And then the equation becomes phi double prime plus 2. Now I define this curly h to be the Hubble parameter defined in terms of this conformal time. This is positive. Now, okay, so it's prime means d phi by d eta. Here, I remember that everything is has a label k. What else? When I say k squared, it means norm squared of the vector k. And sorry, let me just give you one more definition and then answer the question. And then when I say curly h, that is a prime over a. And this is just a times the usual non-curly h. Yes?
I think I'm confused because you said now you're considering fluctuations, spatial fluctuations of the field.
Yes.
But this does not mean that you have changed the background to consider perturbations on the metric also.
Oh, good. Sure, I have to consider all fluctuations, both in the metric and in every field that I'm discussing. However, I'm going to study the linearized perturbations. I have a background solution. On that solution, I'm considering linearized perturbation. Or at the level of action, it means that I look at quadratic part of the action in terms of those fluctuations. Now, if I want to do a full treatment of the problem, I should perturb all fields and metric. Now I'm just doing some toy model, just to give you an idea of some, just to understand some general properties. But then, yes, of course, in the full treatment, also metric has to fluctuate. Yes. But you should remember that this part of the story wouldn't change much because this is already quadratic in fluctuation. So if I want to study linearized perturbations, there might be metric fluctuations somewhere else, but doesn't matter here. If I had some background solution, then they would mix with each other and there will be some complications.
It's just because I thought this phi is the background plus the fluctuation.
Oh, no.
But this is just the fluctuation.
This is just the fluctuation. Okay. Yes. That's why I use this curly phi. So that's, yeah. So this is, imagine this is just a different field. At the moment has nothing to do with inflaton. I'm just considering a scalar field that lives in a Far-W cosmology, has no background value, and I just want to study its fluctuations. So what I'm doing is I'm going to the momentum space. I want to see what is the behavior of the modes in this momentum space. And then I use this conformal time to get to this equation. Yeah, it's too busy, you know. So I use conformal time to get to this equation. And now this equation looks nice because if this term wasn't there, then it was just the usual wave equation that we would write in Minkowski. So therefore, we can consider Now, therefore, here we can consider two different regimes. One regime is when k is much larger than this. Yeah, what is it called? Is it called? Yeah, I guess this curly H is called conformal Hubble, but I'm not 100% sure. Does anyone know? No. Okay, and I'm going to call this maybe curly H, maybe just H. But so so we are these two different extremes that are interesting to focus on. One is the simpler one, when k is much larger than h. When k is much larger than h, then the solutions are more or less the same as in Minkowski space. So phi k of eta, or let me just write. Let's talk about the solutions. Let's denote by the solutions by f. Then there will be a positive frequency solution, fk of eta, of this equation that would be approximately given by e to the minus ik eta, with some coefficient c. And now, of course, there would be the other independent solution of the equation is the complex conjugate. So these are solutions which are very fastly oscillating, right? Because so this is the phase of the equation, right? If I look at the variation of the phase as a function of time, as a function of the physical time, so I look at d by dt. So imagine I am an observer. So what experiment are we considering? Imagine this is t, or this is the word line of an observer who is sitting there, and then this wave is passing by. And what I want to measure is the frequency of this wave that is passing by. How do I measure the frequency? I look at the diagram for this wave. It has a phase. I take the time derivative of the phase. It gives me the frequency. The time derivative with respect to the time that my clock measures. So this is t is the physical time. So d by dt of k eta is what is it? This is just the definition from the definition of the conformal time, this gives me k over a. So this is the frequency that I measure. So for instance, if I consider two observers, one is sitting, so Alice and Bob. Alice is here, Bob is here. Alice is sending a signal to Bob, a very high frequency signal. Then there will be a change in the frequency of the signal that Bob is measuring compared to the one that Alice is sending. What is the change? Omega A over omega B. Imagine Alice and Bob are living very far away and at very different times in cosmology, different times compared to the cosmological time scales. Then the ratio of omega A over omega B, so this k is just constant. These modes with a given k are remain at that same k. That's in fact why we use this momentum basis, because k is the good constant of motion. So k is constant. Omega A over omega B is just given by A B over A, and this is essentially, this is just the redshift that we Raoul talked about. So we can, the frequency of the Mohs ratio, but notice that if we are, let us consider this condition, this k much larger than h. What happens is that if we are in the regime in which, well, let me look at this ratio, for instance, k over h. And let's see what happens with the time dependence of this ratio. So this k over h tells me that whether my fluctuation is sub-horizon or super-horizon. If k over h is much larger than 1, it means that we are in the phase in which the mode is fastly oscillating. So now I can ask with time whether this condition remains satisfied or at some point it changes. So therefore, I should look at the time derivative of this quantity. And the time derivative of this quantity, this curly h, if we remember that from where, okay, so I erase it. This curly h was a prime over a, which is just a times h. So this is nothing but the same parameter, the same quantity that we were talking about in the morning when we talked about this flatness and horizon problem. This is the quantity that is related to the co-moving radius or the particle horizon. So this is the quantity that if we are in a phase of cosmology with W larger than minus a third, like the radiation dominator or matter domination, then this time derivative is going to be positive, larger than 0, which means that if I send a signal which is oscillating very fast, meaning that k is much larger than h, then as time passes, that condition remains satisfied. It becomes even better. So when this is satisfied, we call the mode being sub-horizon. Why do we call it sub-horizon? Because we are talking about modes that are fluctuating or have some k modes which are much, much smaller than the size of the distances which are relevant for the cosmological scales. So these modes are called sub-horizon and they are oscillating. And we learned that in the phase when W is larger than minus a third, sub-horizon modes remain sub-horizon. They even become more and more sub-horizon in a sense. On the other hand, if k is much less than h, the property of the solutions would change. Then this term is negligible in this equation. And so we have two solutions of this equation. The solutions depend not on the exact time dependence of h, but one of them, you can easily see that is a constant. So there will be one solution which is a constant mode. Normally, this constant mode is the largest mode, meaning that the other solution decays in time. Usually, the solutions are called decaying and growing solutions. So for instance, here, the growing solution is a constant, and then there will be a decaying solution. Now, what happens is that if W is larger than minus a third, so if we consider model like radiation dominator or matter domination, the modes that are another thing is that these modes are called super-horizon. Super-horizon because if I consider the wavelengths of these modes, the wavelength is much larger than the characteristic cosmological scales that we are dealing with. So these are two very different regimes, sub-horizon modes versus super-horizon mode. Sub-horizon modes behave as we expect waves to behave in Minkowski, while super-horizon mode have characteristically different behavior compared to modes in Minkowski. In particular, they can be just constant or decay in time instead of oscillating. So when we are in the phases with W larger than -1/3, what happens is that super-horizon modes, or this condition, so remember K over H is positive. It means that the modes which are super-horizon gradually become sub-horizon. That transition is called crossing the horizon. So this is called horizon crossing. So for instance, if we had a super-horizon mode which was constant, it crosses the horizon, it becomes a sub-horizon mode, and now it starts to oscillate. While the sub-horizon modes continue to oscillate. Now, on the other hand, if we are in the, I finished just, I'm not gonna go over there. On the other hand, if we are in the accelerated expansion phase, like inflation phase, what happens to the modes is the opposite. Because if you remember this ratio, this quantity during the acceleration is going to be negative. The accelerated expansion means that this time derivative is negative. And what that implies is that modes which are sub-horizon are becoming super-horizon. Normally, we say that they get stretched to super-horizon scale. So they start inside and then move outside. So it's exactly the opposite. Okay, I guess this is so now later in tomorrow's lecture, I'm going to focus on these fluctuations of the inflaton field and then also metric during inflation, in which we have this phenomenon of sub-horizon modes getting stretched to super-horizon scales, and see how that leads to production of fluctuations that we think are the origin of all inhomogeneities that we see in the universe. Okay, I can stop here. Yes?
I think this is related to what you just said, but when you get these super horizon modes that are constant, aren't you getting the same problem that motivated inflation in the first place? Like, you don't want things that are super horizon to be defined to be the same value if they are not causally connected. Like this.
Well, what happens is that well, this is something that we are going to discuss more. But what happens is that during inflation, we have, in fact, it's exactly the opposite situation that compared to the one that we are dealing with in late cosmology. We have modes which are inside the horizon, and then they stretch outside. So what is the question? For instance, they were in causal contact, and then they get stretched to regions that are not in causal contact anymore.
Okay, I think this. Just that if you specify the super horizon initial conditions to be constant, then this explains it, because you are saying that the super horizon scales are actually come from the super horizon that are stretched out. But if you just start with something that is constant, then you get the same problem, right? You are specifying an initial condition that isn't causal.
The interesting point about inflation is that, right, that was the whole point of this discussion. The interesting point of inflation is that as opposed to usual FRW cosmology, in usual FRW cosmology, the sub-horizon fluctuations that we see, they come from superhorizon. Therefore, you need a theory of initial condition to determine them for you. So you have to, something should determine the initial condition for those superhorizon fluctuations, because what we are going to see today, which are inside our horizon, they used to be outside. It's exactly the opposite in the case of inflation, because you do not need a theory of initial condition. Inflation naturally provides it for you, because anything that is outside the horizon was originated inside. And when they are well inside the horizon, we think we understand well enough quantum field theory in Minkowski to be able to set their initial condition there. We don't need something beyond the normal quantum field theory that we understand to set the initial condition.
Okay, thank you.
Any other question? Okay, so let's thank again the speaker. So there is a coffee break, and then at 4 we come back here for the discussion.